Okay, we're back to talk about torque. And I know that when you start talking about physics, kinematics is kind of the foundation of everything. It's kind of how everything gets started. But as far as rotational motion goes, many things that we're going to do build off of the idea of torque. Okay, so it's not particularly hard. I will admit the first time that I encountered torque when I was in high school, I admittedly didn't understand it very well, but when I saw it again in college, I was like, I don't know what I was making such a big deal about, okay? It's not too tricky of a subject to learn, even in a short period of time. So, moving right in. The definition of torque is a twisting or rotating of an object as a result of a force applied to it. Okay? Now, you might be thinking, hey, that sounds kind of like a centripetal force, and really we're not talking about the same thing here. Okay? Matter of fact, so for one of the examples I can think of, for instance, let's see here. Yeah, like a string keeping a ball moving in a circle, or the Earth going around the sun due to the force of gravity. I believe, off the top of my head, I've never thought about this before, neither, or at least in this context I haven't, neither of those examples involve any torque being applied, even though you do have something rotating as a result of a force. So, this can be, well, you know what, why don't I just show you an example, okay? Let me grab my example here. And I'm going to adjust the camera so you can see this. Okay, so here's my example. I've got my laptop sitting here, right? Okay, the laptop is open. Now, let's say I want to close my laptop screen. I want to fold that down onto the keyboard. Now, the most obvious way to do this is for me to simply push up here, right? Well, let's think about all the different ways that I could try and do this, or what might make this easier or harder. Obviously, the harder I push, the easier it will be to close. If I just take, my pinky finger and push on this, it's going to be a lot harder to close it than if I take my whole hand and I simply just move it down like that. Okay, so that's an obvious one. There's a couple other factors that are going to influence how easy it is for me to close my laptop. One of them might be where I put my hand or finger to close it. It's very easy for me to move my laptop if I put my finger up here. What about if I put my finger in the middle of the screen? Okay, you can see that it even just looks like it's resisting a little bit more. It takes a lot more force if I put my hand there for me to close than if I put my hand here. And to go even farther, what if, let's say, I try to close from down here? Doesn't matter how hard I push, I can't really get it to close if I push down here. And the one thing that you'll notice is by pushing down low, I am pushing closer to the hinges here, okay, the what you might call the axis of rotation. So where I apply the force for the first time seems to be making a difference, and that's very interesting. One other factor that I want to talk about is not necessarily just the size of the force or where I apply the force, but the angle at which I apply the force. We already said that it's very easy to close the laptop if I put my hand up here and push this way. But if I push down, doesn't matter how hard I apply the force, I'm not going to be closing it. Even if I push at an angle, it takes a lot more force for me to close when this is at an angle than it does if I apply the force this way. So one thing I want you to notice is the angle that I'm pushing at. You might say as a even that you're pushing at a right angle relative to, well, the screen, I guess, or more correctly, you're pushing at a right angle relative to the line going from the axis of rotation up to where you're applying the force. So I want you to think about that for a second, okay? So we see that to twist, in this case, twisting would be what's kind of happening to the laptop. It's twisting or turning as I close it, okay? It's rotating. There's a lot more to think about than just how hard I push. Okay, let's get this situated again. Okay. Usually in class what I do to demonstrate this, and maybe I'll do it for you guys, is I have a mass on a meter stick, but I don't have either of those things up here. So let's talk a little bit about what factors affect how much an object twists or turns. The first one, I would argue, is how strong the force is. Or in other words, the magnitude. Okay? The magnitude of the force definitely, and that makes sense. If you want to get something to twist a lot, you apply a strong force to it, but that's not the only factor in this game. The second one we saw was that where the force is applied in relation to the pivot point, or a slightly more physicsy word for that, the axis of rotation. We saw that where the force was applied makes a difference. You can apply the same force at the bottom of the laptop screen as opposed to the top, and at the bottom is not going to cause that much twisting or turning, whereas applying that same force at the top seems to apply much, much more. And the last one, the last factor that seems to affect this, is the angle at which the force is applied. We saw that pushing perpendicularly to the laptop screen, or I guess you could also say perpendicular to the line between the axis of rotation and where the force is being applied, seems to make this easier. Makes it turn more easily. Maybe you're providing more torque. So how can we calculate the size of an individual torque? Because we want to calculate this. Well, here's the equation. It starts with a symbol you've never seen before. This is the Greek letter tau. I don't want you calling it T. I might mess up and call it T on occasion, but this is the Greek letter tau, and you should refer to it as such. This is the equation for an individual torque. Tau equals R times F times the sine of theta. And I'm going to define all these for you. Tau is the symbol for torque. Any individual torque. You can have many different torques acting on an object, in fact. Tau is the symbol for one individual torque. R, you're used to saying as the radius or maybe the distance between the centers. It's something else this time. R is the distance from the axis of rotation, which I'm going to abbreviate AOR, to where the force is applied. Okay? And there is one other note I'm going to make with this. If the object is in what is called rotational equilibrium, which is essentially a fancy way of saying that all of the torques on this object cancel out. It's kind of like saying all the forces cancel out, so there's no net force. I'll get down and talk about net torque in a little bit, but essentially, if there is no net torque, if the object is in rotational equilibrium, then you get to choose the axis of rotation. And that freedom is nice. Just like sometimes you get to choose the zero height in, let's say, a conservation of energy problem, getting to choose the axis of rotation can be very useful in a torque question. So that's what R is. R is the distance from the axis of rotation, or more specifically, it's a displacement. I really should be saying displacement. So I'm going to scribble that out. Displacement. Okay, hopefully you can read that. The displacement from the axis of rotation to where the force is applied. F is the magnitude of the force applied. The force that is causing the torque. Theta is probably the trickiest to understand, but if you can get this definition in your head, it's not all that hard. It is not necessarily, it's not in radians, and it's not necessarily the angle that is given to you. I like to say that theta is the angle between R, the displacement, and F, the force if each vector started from the same point. In other words, if you wrote them tail to tail. And we've written vectors tail to tail plenty of times. Okay? So it's the angle between R and F if each vector started from the same point tail to tail. And we'll see examples of this in the following videos. Yeah, but it's a little strange to think about right now. I will give one other option or recommendation, and again, a lot of these will make more sense when you're actually doing the problems. If this angle is not obviously 90 degrees, then consider using a method I will teach you in a couple videos that I will call the line of action method. Okay, I'm going to take a quick pause there and go back and look at this equation. The torque is what all these things multiply. That's the product of all these things. And torque essentially, again, means a twisting or rotating of an object as a result of a force applied to it. So if you have a bigger torque, you have a bigger twisting or turning impetus, I guess you could say. So it makes things easier to twist or turn. If you increase R, if you increase the distance from the axis of rotation to where the force is applied, you get a bigger torque. It's easier to twist or turn things. Think about why we put door handles opposite the hinges. We don't put door handles on the same side as the hinge. It would take tons and tons of force to open. You wouldn't get that big of a torque by pushing where the door handle is. So we put door handles opposite the doors. Obviously, a bigger push or pull is going to lead to a bigger twist or turn. The sine theta part is a little trickier to see, but remember when I was checking out the different angles at which to push, it seemed best when I was pushing at a right angle to the line from the axis of rotation up to where the force is. That would correspond, since it's a right angle, to 90 degrees, and the sine of 90 degrees is 1. And you know that sine of theta can never be bigger than 1, so that means that if this is 90 degrees, the torque is as big as it's going to get. Now imagine that, do you remember when I pushed straight down on it? That's like saying the force and the line between the axis of rotation and the force application point are either parallel or anti-parallel to each other, either 0 or 180. And that would produce a sine of 0, which means no twisting or turning. Okay? So depending on what the angle between those two vectors is, you can vary the size of your force. Okay, so that's how that equation works. Let's talk very briefly about the units. The units of torque, the units of R are meters. The units of F, force, are newtons. And sine theta just gives you a number, okay? So the units end up being a Newton meter. And I do want to caution you, because something else that you've used could possibly have units of a Newton meter, and that would be joules. This Newton meter, even though it looks like it, is not the same as a joule. This is not the same as a unit of energy. It's its own unit, okay? I don't want to get into the details of why this Newton meter is not the same as a joule, because number one, I don't think I really remember why, but they are not the same. The units of torque are Newton meters. They are not joules, okay? Do not use joules as units. And then just one little kind of housekeeping thing. If a torque causes or tends to cause an object to rotate clockwise, it is negative. If it tends to cause it to rotate counterclockwise, it is positive. So we do have a convention. You don't have to follow that, but that's pretty typical. This is the convention for how to label your torques, because you could have positive torques, you could also have negative torques. I'll close this video by looking at the correspondences between what I like to call the linear variables we've seen so far and the angular variables we've seen so far. So far we've really looked at these. We've seen that the distance, the linear distance term that we have used so often, well, in angular motion, that kind of corresponds to, instead of talking about the distance in meters, we instead talk about the angular distance, or the amount of rotation that's happened, and their variable for that is theta. The linear speed, how fast something covers a certain amount of distance in some amount of time, is instead replaced, when we're talking about angular motion, by how quickly something rotates. So v gets replaced, or it corresponds to omega. We can also have an acceleration, the rate of change of our velocity, our linear velocity, and that would correspond to angular acceleration, which is alpha. Okay? And then the last one that I want to talk about is when we talk about forces. And again, these aren't direct equivalencies. They're more just like, I'm not saying a force is equivalent to a torque. What I'm saying is a torque is kind of like the angular version of a force. It does sort of the same thing. They are not the same thing. Matter of fact, torque is dependent on force, but it's along the same ideas, even if they're not exactly the same thing. Okay? So distance corresponds to theta, angular distance, or displacement. V corresponds to omega, A corresponds to alpha, and forces, F, correspond to theta, which is tau. I'll be back later to talk more about forces.